So this project and this talk is part of my master's degree thesis in artificial intelligence and data engineering at the University of Pisa, and it regarded a framework for training reinforcement learning agents based on telescope data. So the idea is to build artificial intelligence based on examples of interactions in a dataset between a telescope and the sky in order to achieve self-driving telescopes. In particular, we want to go towards these autonomous entities that may help to revolutionize astronomy. In fact, we have the bias of humans designing the schedules for telescopes such as JWST or LSST, which are designed and engineered to capture data. And this bias can be overcome with an autonomous entity able to automatically determine where to point. So we want to optimize the flow of telescopes as sky watchers. And to do that, we start from the optimization of a sequential schedule. So given a discrete list of sky locations to be visited, we wanted to build this entity with AI that could move from site to site or to gather the data with the highest quality and decide on its own which sites to visit in a certain moment given the discrete set available. And to do that, we use reinforcement learning. This is a paradigm of machine learning that are able to train an autonomous agent that behaves optimally in a given environment. In our case, the environment is the sky, and the environment is going to have at a certain time t a state s of t. This is going to be related to the agent, which is what we want to optimize. And the agent should map the state to an action, where the action a of t will go again to the environment. The environment will respond with a new state, st plus 1, and a reward, plus 1. The reward will make the agent understand how good was that action in the previous state, s of t, and the new state will use this loop to determine the next action. And the idea of the agent is to maximize the expected cumulative reward over time. And as we can imagine, the environment is not a real environment, but is simulated. It can be an online simulation tool, so a set of algorithms that simulates the sky, but it's very hard to be achieved due to several factors such as stochasticity in the weather. And our framework is that use an offline dataset. So an examples of interactions between a telescope and the sky, it can be any kind of telescope for which we have a dataset, and examples of state or site, action, a consequent reward, and the next state. And here we have an example of how it could be this offline dataset that can be provided to our work. So in our environment that we used, we have a state space that contains some metrics related to the telescope, the moon, the sky, the sun. As we can see here, many variables that can be sensed by the telescope that the telescope can know. And together with the values of a state, we may have multiple rows with the same state associated with some actions. And the actions is going to be a right-hand side here that determines an X pointing in the sky. And associated with a pointing, given the state, we have the example of the reward using t-effective variable. T-effective is a measure of the depth of the image and measure the quality of an observation. And together with the reward, we have the new state we saw before. And we need a dataset with this structure to use it in our framework to optimize the agent. So given a state, we have multiple examples of actions, rewards, and the agent will learn the proper mapping. And this mapping is typically done with a neural network as function approximators. The neural network will have the state as input. And I forgot to say that the state space can be chosen in our framework. So according to the variables that you can sense with your telescope, you can directly determine these variables, while action space and reward are set. And as output, we're going to have a distribution over the action space. So the probability of taking each action, where the action is nothing else than a site, given the state. And the proper weights and biases of the network should be learned in order to have the right mapping to choose the best site in each state. This is an example in particular of policy-based methods. Our framework, though, take the offline dataset with a training buffer and use it as an environment with proper logic. A model trainer will use this dataset, a deep neural network structure that can be chosen, as some experimental configuration in a YAML file that can be provided here. and providing output that we're going to see dataset splits, network checkpoints, and TensorBoard logs, while a tester model will use, again, the environment and the checkpoints produced during training to generate statistics to compare reinforcement learning algorithms. And here we have an example of our command line interface of the framework. We can set the algorithm, dataset, and the maximum number of iterations. We have an example here. So we're going to see some parameters, hyperparameters of the algorithm, the structure of the network, and all the training process that can be really seen also with TensorBoard, because checkpoints and TensorBoard runs, as we saw, will be generated, and using a proper command on TensorBoard to see all the metrics we plot. Here we have an example of the average reward during training. And as we saw, more checkpoints will be generated, and the tester model can be used again with a command line interface based on a checkpoint path. And the dataset that can be, for example, a test set time to generate statistics. We have different algorithms supported based on the PyTorch AgentNet library, and several features were adapted for the cosmological background. And since we have few time, I wanted to particularly focus on one of these features, is rendering. We can start to run the command, and rendering will allow us to visualize and interpret the artificial intelligence after training. We're going to see a plot that shows the importance of each feature, of each variable in the state space for the agent. We're going to see the action chosen by the framework, by the neural network that we trained, and all the possible instead sites available, just with the sites proportional to their reward, so that to their quality. Then we're going to see the maximum reward we could have gathered with respect to the minimum and the one that he has gathered. And the same reward, we can see it with a trend normalized between 0 and 1, with a mean value and the standard deviation. And in particular, this is going to be live using the command we saw before. I don't know if you can see it. I have pink on top, but yes. And this way we can monitor and interpret the artificial intelligence some way in order for people to, let's say, use the artificial intelligence and have a more chance of it, because it's an open problem in AI. There are other features as I saw before, but to conclude and wrap up, this was focusing on development of a framework based on any offline dataset that can be used to train RL agents. It will be soon available on GitHub, and results on the Stone Age Observatory simulation dataset showed convergence property. This is a dataset of a telescope primarily in California. And as future work, we want to go towards an online environment instead of an offline dataset that could increase the amount of data available. And the continuous action space may let the possibility instead to use the whole sky instead of a discrete set of sky locations. Thanks, and if you have any questions, I'm here to answer.